let's talk about love again. Love is what makes you go the extra mile. So when Luca Di Bartolomeo, he's probably from Italy, so Rome, the speaker of the following talk had the idea to port an existing x86 static binary rewriter to ARM64, things turned out different than expected. It must have been a real love story. Luca was all in. Today, after more than 2 years, ARMore, we learn what this relationship is about. I'm excited to hear what is going on in the binary bedroom and what the outcome of this love story is. Let's talk ARMore. Please give a lovely round of applause to Luca.
Hi everyone, I'm Luca, nice to meet you. So today we talk about binary writing on ARM. And what I would like to present to you is this tool we developed called ARMore, which is the first one being heuristic-free, which is the important part here. Why is it the first? You're going to see in a while why no one did this before, unfortunately. So a disclaimer before we start. This presentation is going to contain assembly. A bunch of assembly. And I know everyone hates looking at assembly, but I did it for the past 2 years, so you're going to get it for the next half an hour. Sorry about that. Now, what is binary writing? Very quick recap. It's a process that allows to do late-stage code modifications to a binary, which means I have a binary. I don't have the source for some reason. Maybe I was not supposed to have this binary for whatever reason. I want to change its behavior, right? But I want to not break it, right? So as an example, maybe I want to change its architecture. And the whole process looks like this. I get a bunch of assembly and I need to transform it into other assembly that works more or less in the same way as before, right? And the key challenge is in not breaking stuff. Now, some quick necessary background you need to be aware to understand this talk. You need to know that x86 is an architecture. You need to know that ARM64 is another architecture. You need to know about the presence of pointers that are unfortunately everywhere, and they really fight against you, right? You miss one and it's game over. And then there is another important concept in binary writing, which is fundamental to know, which is the concept of pre-tired. The feeling of succumbing to exhaustion after thinking of everything you have to do, but before doing any of the work, right? Do not confuse this with laziness, okay? Very important. Now, why I went into this rabbit hole? Because when I was starting my PhD, my advisor sent me a letter. It was kind of like this, right? So we have this existing, can you still hear me? Maybe? Okay, I will shout. So existing x86 static binary writer, that was cool, and we wanted an ARM64 one, right? It was supposed to be a very easy project, you know, like in Binary Ninja, when you add a new instruction set, you spend a couple of afternoons implementing instructions lifting to an hour. Unfortunately, this was 3 years ago, and it didn't really pan out that way. So, why do people do binary writing? Who cares about it? The use cases are multiple. Some people do it for hardening, because maybe you compiled a binary, but you forgot the mitigation, and you want to add it after you lost the source. A more popular use case is profiling. In fact, Valgrind and NGB are kind of doing binary writing when you insert a breakpoint. This is more or less what happens. There is translation. This is very popular. QEMU is basically, this is what it does. And, but the most popular use case by now, the hot stuff, is fuzzing, right? Because we want to fuzz closed source binaries, and we want to add coverage instrumentation to that. This is what AFL QEMU does, okay? An important distinction we need to say is that binary writing could be static or dynamic. The difference is, do I change the code ahead of time or during execution? I will not go into depth of this, but dynamic is usually better because you have runtime information. When I'm changing the code, I can look at the content of the registers, I can look at the state of the memory. I have so much more knowledge to fix pointers and other stuff that will break. the big disadvantage, as you can see in the last line, is that it's slow, because I need to stop execution, think about what I have, and then change the code. While static happens ahead of time, unfortunately, there are many issues, and obviously, we're going to look into the bad one, right? So, what was the starting point? Was this tool called RetroWrite. It was presented at the last CCC, actually. There is a talk about it, it's very interesting. The key innovation of it is that it used relocations to detect pointers that are in data. We'll see why this is important. And ARMore was supposed to be an extension of this, right? Using the same concept and just add a new architecture. Unfortunately, no. Unfortunately, we figured out that the challenges ARM presents are different, so different that we had to start from scratch, redesign the whole thing, and now it's a completely different project that has different characteristics and so on. Why is this the case? For one reason, mostly. ARM, like every other RISC architecture, is fixed size. Right? And you may think, but this makes stuff easier, right? Disassembly is super easy on a fixed size instruction set, right? You don't have the problem of variable size instructions and so on. So why? Well, because unfortunately, very, very often, a binary wants to put a pointer into a register. And while on x86 it is very easy, it looks like this. It's a single instruction. On ARM, you cannot, because you don't have enough space. You only have 4 bytes. Especially on ARM 64, pointers will not fit, right? So if you go look into the very famous ARM, the ARM reference manual, among the 7,000 pages you have, the ARM developers tell you, you have 2 options to solve this issue. The first one is you use literal pools, which is very easy. You just store the pointer in raw data and then you load it back. The second one is more creative, it's more fancy, you know? Why do you need to use a single instruction to build a pointer? Why not multiple, right? Not both. And as you might guess, this is where problems start, right? So let's look into this a bit more in depth. So literal pools looks like this. You have LDR x0, then you use this weird syntax equals pointer. This is a pseudo instruction. The assembler will store a pointer in raw data for you and then generate the relative load for you. And this is very easy to deal with, right? Because 99% of the cases you have relocations for that. Not a problem. This instead is a problem. Now, I need to stop for 20 seconds and make you really understand the process here, right? This is the key of the talk. Now we have 2 instructions, right? The first one is called ADRP, stands for address page. Now what does it do? It stores the base address of a page into a register, okay? It is PC relative, but has a huge range. I don't remember how much, but you almost always are covered. If you are too far away, then you use a literal pool. But then you're left with the offset inside the page, the last 12 bits. And for that, you're free to use whatever you want. Usually arithmetic instructions, but there is no strict rule. Now that you know all the basics, let's look a bit more in depth in the challenges I showed you before in the table. So let's start from the first one, a very classic one if you ever did any binary writing. The problem is that the average binary is a huge mess. Even something that comes out of the latest compiler that should be very easy, your main.c, printf hello world, is not as easy, right? And the first challenge is distinguishing between code and data. They really look alike, right, when you look at the binary. You don't have symbols, obviously, right? You cannot use debug symbols. Why? Imagine you have this assembly, then the bytes will look like this. There is nothing that tells you that there is a string in the middle of the instructions, right? Now, the problem is, as soon as you interpret a string as instructions, when you do binary writing, you're going to insert instrumentation. You're going to change instructions. So you might end up changing that string, right? Maybe it is fine. Maybe you don't break stuff. But in most cases, any mistake you do will lead to a crash. right? Very, very often. Because the most likely case is not that in the middle of a code there is a string, in the middle of a code there will be a pointer, right? And as I told you before, you don't fuck with pointers, right? You cannot touch them. So this is the first challenge. This, however, is not relative to ARM. This is also relative to x86. It's a very long, old challenge. But this new one, the second one, is unfortunately spawned by ARM. And it's about recovering pointers. The problem is that as soon as I want to add a single instruction inside the binary, the address of everything else afterwards will change. Okay? So I break every single reference to anything that is after that. Which means in static binary writing, your objective is to recover every single pointer inside the binary. All of them. It's super unlikely that there is a pointer which is just dead, it's not used. More or less each pointer will be used at some point, and if it's wrong, you will crash. Now, there are two types of pointers in ARM, right? Literal pools and pointer constructions. So literal pools are easy because almost always you are looking at a position-independent executable, which will have one relocation for each pointer that is stored in memory. And so you can just look at the relocation table and figure them out. If it's not position-independent, you have another solution I will explain later. Now the problem comes with how do you detect pointer constructions? And yeah, that's the 2 years here. So why? Because compilers, when you tell them, look, just grab a reference to something, the code they will generate, especially if you turn optimizations on, is yeah, very creative. You see stuff like starting a pointer construction, then saving it on the stack, and then resuming ages later, right? And then finishing the pointer construction. This, to solve statically, is a huge pain. You need to keep track of what stuff goes into the stack and so on. But the most favorite hobby of compilers is the following. You have a function, and you say, OK, now let's build 15 pointers, all at the same time. And we're going to reuse partial calculation, mix and match between them. And here also, recovering them statically is another huge pain. You need to do kind of symbolic execution, stuff like that, keep track of where goes what. Lastly, there is also switching registers in the middle of the construction. As you can guess, there is all kinds of stuff you can do, right? Compilers are really free to do whatever. So I bet that many of you in the audience, after seeing this, will say, OK, look, but what's the problem here? Why don't you just do data flow analysis? Obviously, right? Why don't you just track where data is going where? And my answer to that is no. No. We tried, it doesn't work. It doesn't work, why? Because any mistake is fatal. And data flow analysis will never be 100% precise. You don't have the computation power to do it, and there are so many edge cases you will never cover them all. We tried pattern matching. We said, OK, maybe compilers have a finite set of pointer construction patterns they will generate. Maybe there are 30, there are 40. I look at 1,000 binaries, more or less I have all of them. No, there is no way. There are too many compiler versions, options, and so on. No. We tried the data flow approach. Yeah, that also didn't work. Any mistake is fatal. This is challenge number 2, how to recover the value of a pointer and rewrite it to preserve its target. Now we move on to the final one, challenge number 3, also very painful, which is jump tables. Jump tables, why? Because you guys, C developers, really, really love using switches. Every function has a switch. Why not 2, 3 nested switches? Why not? And this, when you look at the disassembly, it's bad. Because a jump table it doesn't store absolute pointers to the cases. It stores relative offset from the base case to the various cases, right? And it's stored in raw data, and it's impossible to distinguish it from other data. And that's the same as pointers. You need to detect jump tables. Why? Because if you insert instrumentation between the cases, right, then those offsets will change. This is how a jump table looks in raw data, x86 and ARM. You see those are relative offsets, they're not absolute pointers. On the right you see that each case is 2 bytes big. This is not force, it could be 1 byte, it could be 4 bytes, depends on how the compiler feels that day. It is really impossible to detect, oh, this is a jump table. And the worst case is that this is not a new problem. People have been doing this for years, trying to detect jump tables, right? Even if you fire up IDA Pro, it will still fuck up on some jump tables, right? Even state-of-the-art tools are not good enough. Even the best techniques we found, they are never 100% precise. For example, this is what a jump table looks in ARM. You can see the last instruction is the indirect jump. And what you need to do is need to go back and figure out, oh, where is it stored in memory? And in fact, if you see the first 2 instructions, it's a pointer construction, obviously, because why not? And you need to figure this out. We tried for so long to build a fancy backward slicing data flow thing. I wasted so much time on this. It doesn't work, right? I mean, it works 99.5% of the times. But the jump table you miss, right? It's going to give you hours and hours and hours on debugging, and it's an edge case you didn't predict. It's not going to work. So we now move on to what is the solution to this, right? And it's using pre-tiredness, okay? It's very important. Because what we saw is that there are many solutions that are either infeasible, take way too long to implement, they are not realistic, or they are not fully precise, okay? So our intuition was just, can we avoid the problem? Can we run away from the problem? And it works like this with a few hacks. I'll show you. So the first thing we do is when we rewrite a binary, we use layout replication, okay? Layout replication is an old technique. It's nothing new. It was used in x86 before. How it works is that the binary you produce, you use a linker script thingy to make sure that each section will be exactly at the same address as before, okay? Now, how does this help? Is that if there is a literal pull pointer in raw data and you don't detect it, it's fine, because stuff will be at the same address, right? This is very easy, very intuitive idea. Obviously, I know that people who are paying attention will tell me, this doesn't work for .text, obviously, because I put instrumentation there, right? And stuff will change, okay? But we'll fix this later. We just start from this base, okay? Everything is at the same address. Unfortunately, this only works for literal pools, not pointer constructions, because they are PC relative, so you cannot just preserve the hard-coded address. You need to fix them as well. Now, how do we make each pointer construction target its replicated layout? And this what saved us was the ARM again. In the 7,000 pages, there was a box saying, look, the program counter register, actually, it's a special register. It's not general purpose, obviously, but in particular can only be read by 2 instructions, which are the following. The branch and link, which is the same as the call on x86, which reads the PC to store it in the return address, and the address page I showed before. Okay? What does this mean? This means that every single pointer construction needs to start with an ADRP. There is no other way to load a pointer which is far away, PC relative, without an address page. So this means that if I manage to preserve offsets inside a page, I can just fix the first ADRP and not care about anything that happens in the rest of the pointer construction. That huge mess of arithmetic instructions, I don't care about it, right? This means that I don't need to do any fancy static analysis, any data flow, anything else. But still, code pointers are still broken, right? Because the text section move around. And for this, we introduced what we call the rebound table. The rebound table is nothing else than a new section, a new code section, which, as you can see, stands exactly in the same place and of the same size of the old text. Okay? And the code instead is moved somewhere else in the instrumented text you can see below, very far away, in another place in the virtual address space. How is the rebound table? Is incredibly simple. It's just a sequence of branches. Why? Why does it work why does it work for code pointers? So imagine that now this is the layout of my binary, right? I didn't change any pointer whatsoever right now. There is a pointer construction, and it will make the program counter go in the same old others. So somewhere in the rebound table. But the rebound table, I can build it in such a way that the branch will bring me exactly to the new location in the new text. If I add instrumentation, I just need to change the target of the branches. In fact, you can see in the arrow, there I added a couple of instructions. Pointers will still work, right? Because the difference in instructions I added is going to be reflected only in the target of the branches. So now I have two places in my virtual address space. One where everything is exactly as before, and one instead where I add instrumentation and stuff will move. However, this means that anything you dare reference will go through the old layout, and if it's changed, it will go into the new, through the rebound table. And this, the good thing is that it doesn't only solve pointer constructions, it also solves jump tables, right? Because their base offset calculation will be done on the old address and will be done on the rebound table where all offsets are preserved, no matter what I do with the code. Now, there is a caveat. This costs one branch, okay? Every time I do an indirect jump, I need to go through one additional branch. In our benchmarks, this has like a 1% overhead, though. Almost non-noticeable. However, you're probably thinking there is no way you do this huge mess and stuff still works out of the box. And you're right. You're right. Stuff is broken. In particular, what breaks is binaries that read themselves. They read their code. Because what if a binary tries to read its own text? This is very rare, but happens. Some binaries want to check some themselves. Some binaries want to read some data they stored in text. Not everything comes from a compiler. Sometimes you have handwritten assembly with weird stuff. Forget about doing any kind of analysis to understand, oh, this load will target the text. This doesn't work. Never, don't even think about it. So what do? We do another party trick. This is weird, but actually works, surprisingly. We use XOM, which is a feature added in ARM 8.2, and it's executable only memory, right? So this originally is a mitigation to prevent binaries from scanning for ROP gadgets in the text section. What you can do is that you can set a code section permission to only execute. You cannot read from that. On x86, this is not possible yet, but on ARM 8.2, yes. Now, what do we do with this? We're going to install a segfault handler that will detect if you're doing this kind of shit. And then we're going to give you back the correct data. How though? And this is the bad part. We keep another third copy of the text section. Yeah. So the segfault handler will transparently, magically fix stuff. So you read what you think you were trying to read, and you can still scan for ROP gadgets as before. Now, we're done with the solution of the challenges. A quick showcase of what you can do with ARMore. What we did is that we implemented some instrumentation passes that are automatic. They're just already there. Obviously, there is the fuzzing one. So what is the advantage of using this compared to AFL-QEMU? It's the speed. Because the AFL-QEMU obviously needs to instrument each branch for coverage, right? It needs to do it during execution. If you do it ahead of time, you have a 3x, more or less, speed up. And this is in the best case because QEMU can cache a lot thanks to the TCG cache. If you do another use case which is not fuzzing, probably the difference is even larger, but you can expect 3 times as fast fuzzing. Another cool thing we added is binary address sanitizer, which basically scans for every load and store and adds code to check if you're respecting ASAN red zones or not, which is cool for fuzzing or debugging a closed source binary. And we use this to find a couple of vulnerabilities in the CUDA toolkit. It was the only really interesting and easy to fuzz software we found on Linux closed source ARM. In hindsight, the CUDA toolkit is so bad, I could have probably found many, many more vulnerabilities in those years by myself. But yeah. So I don't have much time. I'll show you very fast how does this work, if I manage to. So, yeah. Hope you can see it. Yeah, perfect. So, what I'm going to try to do is write binls. Forgive me. Perfect. So, let's fire up ARMore. It's called retrowrite because we never change name. So, yeah, what this will do is generate a text file with all the disassembly already transformed to a new binary, right? The cool stuff is that you can open this with an editor, right? And just change whatever you want. This actually works. It's very surprising, but this is not a new thing. It's called symbolization, but I could just change this to 1, and it's going to reassemble. I'm not going to do it because I'm going to break it, but potentially you can just change the binary. And then to reassemble it back, you just pass -a, and it will transform it into a new binary. This is just a wrapper around some linker flags for GCC, basically, to do the layout replication, right? And then you can run this, and it's the same as ls. Let's see if I can actually break it, maybe. I don't know. I don't know what can I change. Let's change this to x1. I'm not sure this is going to do anything, but maybe it's going to break ls. Perfect, nice. Okay, so. So what you usually, the use case is that there are a bunch of built-in instrumentation passes, like for example the coverage, right? This will append AFL-style coverage information after every branch. And maybe I can show you, yeah, for example, here there is a branch. And here there is the relevant code that will put a byte in the AFL map. And there's also the ASAN thing, but yeah. So let's go back. Let me finish. Okay, cool. So this was obviously very simplified. The technical details are in a paper that was proudly sponsored by those 3 non-profits you can see on the right. Thank you very much for them. As acknowledgement, I would like to thank my advisor that sent me the letter, my co-author, my flatmate, my... as I said, this was a talk about love, right? Because, yeah. And also the Hexhive lab at my university is full of amazing people that really supported me during all of this. Key takeaways is that, yeah, binary writing is hard, pointers are terrible, and sometimes you don't need to face your problems directly. You can just run away from them and it works better, I guess. Thank you. I'm done.
Thank you, Luca. That was a lot of love, and I have something special to announce. You want to announce it yourself, or?
Yes, as a special feature for who asks good questions, easy questions, there will be stickers.
So, and we have enough time, I think, for questions. Do you send the stickers also to the internet, if somebody's? So, no, it's just joking, just kidding. So we'll start with microphone number 1, please.
Hi, thanks for the talk. So I was wondering, is there a size limit for the rebound table mechanism? Because how long can this branch instruction be, or how wide can it jump?
There is, and the branch instruction can go up to 128 megabytes, if I remember correctly. So we looked up basically you can write everything up to Chromium. Chromium is bigger than 100. It's the size of the text that matters, and Chromium is huge. Everything else was fine. So yeah, there is this limitation.
Okay, question from the internet, please.
Yeah, the internet wants to know if you, in theory, can start an address construction with BRL to the next instruction, similar to the IP relative addressing in 32-bit x86.
You can, yes. Well, yeah. So there will be binaries that will look at use BL and then look at the return address to decide what to do. There is a way to fix this. We had an option. It's called call emulation. And basically what it does, it fixes these two by changing every branch and link to a normal branch, and then we ourselves push on the stack the wrong return address, so you think everything is fine. But this happens, yes, good question.
Okay, number 2, please. Microphone is over there.
Yeah, thanks for the great talk. So I've got a good question, because you are having the old BSS and new BSS, but does it mean that you may have code that will deal with the old BSS, and you may have code that will deal with the new one? And does it then mean that you may have a desync between the values in there or something like that?
So the new BSS is for the instrumentation. You might want to have additional data, and it needs to go into the new BSS. The old BSS is only for the old code, and
so you're not changing where the original data lies. It always lies in the old BSS.
Yeah.
Okay, that makes sense. Thanks.
Come to the front and collect your sticker. Microphone number 3, please.
Hello, thank you for the talk. How did you fix the ADR instruction? Because I saw the ADRP and BLR, but not the ADR. So
you transform it into a longer ADRP sequence.
Okay, thank you.
Yeah.
Microphone number 4.
Thanks for your talk and the work. So I wonder how much this would be applicable to native binaries or native code, provided I have the space for all the 2 copies of the binary in my ROM and know how it's laid out and so forth.
Wait, sorry, I missed it. Can you repeat?
How this would apply to native code running on some embedded device or so that I can instrument with this.
So it depends. If you're doing ARM32, then it's a huge mess because of thumb. And I will show you some people that are working on this, and they are going crazy, yeah. But it's not applicable. The same technique doesn't work. Because as soon as you have a BX that switches modes, then there is this new huge challenge of, is this code thumb or not right now? And yeah. So no, unfortunately no.
Good, thanks.
Okay, microphone number 1, please.
Yeah, thanks for the talk. My question was, so Chrome doesn't work because it's too big. Did you try Firefox? Did that work?
So Firefox, yes, because if I remember correctly, you can write single libraries, and then which that combined into the main binary. I'm not 100% confident. I did this long time ago, but yes, on Firefox it was kind of working. There is the problem that it's C++, so you need to make exceptions work, which is a huge pain. This is a limitation. I had this additional slide of the limitations. If you use the secondary cursed control flow mechanism, like exceptions, you need to take special care. Like, for example, if you, during runtime, you look at the stack, you look at the pointers there, and decide what to do based on them, which is what libanwind does, then it might break, and you need to handle it specially. Go does the same, and you need special handling, right? But C++ and Go work. Rust still no. I don't think we implemented Rust panics yet. But yeah, Firefox should.
Okay, cool.
Okay, microphone number 3.
I'm curious which of these challenges are really specific to AR64, or wouldn't like most of these challenges also occur in x86? I mean, you might have heuristics, but I think they're also not always going to work in x86. Or maybe in other words, can your solutions also be applied to x86 binary rewriting?
No, the problem is with x86 is that since it's not fixed size instruction, you cannot have the rebound table. Because the cool thing about the rebound table is that every single pointer will target something which is 4 bytes aligned. So I can have branches everywhere, and I'm sure you're going to land on a branch. On x86, you can land anywhere. That's the problem. So you cannot really have the same thing.
Okay, thanks.
Maybe there is a super cursed way of doing it, but we didn't explore this yet.
The next 4 years are waiting for you. So microphone number 2.
Okay, so more of a question, more of a comment than a question. I think that execute-only memory can partially work on other architectures when the page is paged out, because when the kernel decides to load the page, it inspects the flags, the permission flags anyway, I guess. So yeah.
That is true. Yeah, that is true. Thank you.
We try microphone number 1 without microphone.
Okay, test. Okay, thanks for the talk. So one of the advantages of doing static rewriting over writing dynamically is that you can spend more time in optimizations, right? And it would be interesting if you could like optimize multiple instructions into one, while as far as I understand here you need to keep a clear distinction between where one translated instruction starts and the other one. Do you see any opportunities for doing, let's say, inter-instructions optimization?
So we didn't explore this yet. All the optimizations we tried to do were about how do we make the instrumentation we add as fast as possible. So, for example, one thing we did, I don't know if I have it here, was basically, if you want to add, for example, coverage instrumentation, you need to use some registers. Try to use the ones that are not clobbered, for example, so you don't need to save stuff on the stack. We didn't look up into optimizing already existing code. It would be interesting, though.
Thank you.
Okay, thank you very much. Please, again,